Hello everyone. In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and in particular we will continue discussing emission spectra and transitions between energy levels. So we sort of began to discuss this particular idea of emission spectra last time. We discussed how the quantum model of the atom explains what is going on with the production of emission spectra and therefore provides evidence for emission spectra. And we have a little graphic here that sort of continues to highlight what is going on. So big picture, we take a thin gas, we apply a high potential difference to it, that is, we give that thin gas energy. When we give that thin gas energy, the electrons in the quantized or discrete energy levels of the atoms composing that thin gas jump up to the higher energy levels. And when those electrons fall back down spontaneously, they emit photons. Those photons are quantized discrete electromagnetic waves with a particular amount of energy. And that particular amount of energy that they have is equal to the difference in the energy levels of the atoms themselves. For hydrogen, there are a very clear and discrete set of lines. It's worth noting that other elements have their own fingerprint. They have their own set of lines. Hydrogen is easily the most simple, so I use hydrogen a lot to sort of illustrate the point. But the general explanation is the same. So other elements will have different lines that correspond to their different and more complex energy levels. Hydrogen, because it's so simple, has some pretty straightforward energy levels, leading to a very straightforward spectrum. So if we take a look at each of these lines in that emission spectrum, and we can see that both in the visual representation. If you run the actual light through a prism or diffraction grating and spread it out, you will see a bright red line, a slightly less bright turquoise line, and then two not very bright purple or violet lines. And if you plot them as a function of the frequency, and plot the intensity as a function of the frequency, you'll see that that red line corresponds to sort of a tall peak, that turquoise is a little bit under that, and then the two purple lines correspond to not very intense peaks in the violet range. Now, each of these lines corresponds to a particular difference in energy levels, and as it turns out, the ones we can see, known as the Balmer series, are actually transitions not between the higher energy levels and the ground state, or the first energy level. So they're not transitions between all these higher energy levels and that ground state. They're actually all transitions between higher energy levels and the second state. And this has to do with the amount of energy that's released. As it turns out, if you take an electron from, let's say, the n equals 4 level, and you drop it to the n equals 1 level, you get an energy difference that corresponds to the ultraviolet, and therefore we can't see it. Now, it doesn't mean it doesn't exist. It does exist. That emission spectrum still exists in the ultraviolet. It's just that we don't see it if we look at the light, because we can't see in the ultraviolet. The ones we can see turn out to all be related to the Balmer series, that is, the transitions between higher order energy levels and the second energy level here. So, to see this, and to get a sense of how you might calculate this, or predict it, we've got a short example exercise here, which is to calculate the wavelength of the turquoise photon. So, if this were all you were given, all the information you were given, plus the information about the energy levels, how would you go ahead and do that? Well, the first thing is to recognize is that we can figure out what the transition is going to be from the color. If we know that all of the ones we can see are to the second energy level, which transition will correspond to turquoise? Well, let's think about it like this. the smallest energy or lowest amount of energy will correspond to the longest wavelength. Now, if we're seeing a set of sort of colored light here, we've got a red light, a turquoise light, and 2 violet lights. How do we know what transition it corresponds to? Well, that red light will correspond to the lowest energy gap that we can see. And that has to be the n equals 3 to n equals 2 level. So the red light corresponds to the gap between these 2 energy levels as shown in this energy level diagram. The turquoise line, shown here in green for some strange reason, is going therefore to be the next line that we can see. And that'll correspond to the n equals 4 to n equals 2 transition. That is the transition between the 4th energy level and the 2nd energy level. That's shown here. All right? So if we take a look at that, how do we calculate the wavelength of the turquoise photon? Well, the first thing to do is calculate the difference in the energies between the 4th and the 2nd energy level. And if the 4th energy level is at negative 0.9 electron volts and the 2nd energy level is at negative 3.4, then that corresponds to an energy difference of 2.5 electron volts. We then need to convert that electron volt unit to joules so that we can use our E equals HF equation. So we take 2.5 electron volts and multiply by 1.6 times 10 to the negative 19 joules per electron volt, which is the conversion factor. That gives us a value of approximately 4 times 10 to the negative 19 joules. If you set 4 times 10 to the negative 19 joules as delta E, the difference in the energy, equal to Hc divided by lambda, using our E equals HF is equal to Hc over lambda equation, then we can find that the wavelength is 4.97 times 10 to the negative 7th meters, or about 5 times 10 to the negative 7th meters. This is sometimes, or more commonly, known as about 500 nanometers, which corresponds exactly to that sort of turquoise color of the transition. Now, likewise, we can use this technique given any arbitrary 2 energy levels to figure out what the wavelength or the frequency of the photon would be. You figure out the difference in the values given of the energy levels and use that to calculate the energy gap between those energy levels, and then set that equal to h times f if you want the frequency, or hc over lambda if you want the wavelength. You could also go the other way. Given a color, given a wavelength, for example, you could figure out what the energy gap is that corresponds to that color. When I say energy gap, I mean the difference in energy between the energy levels of the atom. Now, these values we've seen before, these all correspond to hydrogen, but you could be given to analyze an arbitrary atom with different energy levels of different sorts.